So we were looking at the first process in XV6, right? So what does it mean? So a quick recollection. Um, when the CPU essentially is turned on, there is a reset, and what we've seen is that there is a small piece of code in entry.s which starts executing, that would then um, invoke start.c and then finally main, right? So all of this essentially sets up the kernel, and in main there are various initializations that take place. So paging is turned on, the interrupts are enabled, and things like that, right? And sometime later the OS is ready to start executing its first user process, right? So we are essentially looking at this first user process where the kernel now spawns a new process which is going to be the first code that executes, right? This new process is called Initcode. The contents are essentially present in initcode.s, and it's going to essentially execute with a PID to be equal to 1, right? So this is with essentially with respect to time. So the pink essentially comprises of essentially indicates that the CPU is executing in supervisor mode. Okay, while when it creates a process, it essentially would shift the CPU from the supervisor mode to the user mode in order to execute this initcode.s. Okay, so this is the first thing. The second aspect to which we can actually visualize this is with respect to the memory, right? So when the processor is booting up and executing in supervisor mode, it essentially creates the virtual address space of the process. The way it essentially creates this virtual address space is by initializing the kernel's page tables, right? And within this virtual address space, you have various things. You have the memory that is essentially mapped into, you have the various devices that are essentially mapped into it, and so on. Okay, so importantly for us, when we are talking about the user process, within this kernel space, or the kernel's virtual address space, we essentially have some attributes of the user process, right? So very specifically, we have some proc entries. So we have a proc entry for this user process. So essentially the proc entry would correspond to the PID to be equal to 1. And as we have discussed in multiple videos at the previously, the proc entry essentially would capture the state of the process, the amount of memory it requires, the files it opens, where the page tables are present for that process, the context of the process, and the trap frame, and so on, right? So out of these things that I've listed, the important thing is are the following. So within the proc entry, we essentially have a pointer to one, the trap frame. So this would be the trap frame for the user process. Second would be the the context of the user process, and third important aspect is the pointer to the L2 page table of the user process. So, the L2 page table is nothing but the page directory for the user process, right? So, these are the three important things that we consider when which is present in the proc and corresponds to the user process, right? Another one thing which I have not mentioned is the aspect of the kernel stack, right? So, everything within this proc entry is corresponds to the user process, but for us today, these are the four things which are essentially critical, right? So, what do we essentially do with this, right? So, specifically, pointer to the page table essentially is used to create a virtual address space for the user process. So, this is the processes virtual address space. So, within this virtual address space, we essentially split it into two parts, right? So, the most portion of it corresponds to user mode. Let me this is essentially configured to execute in the user mode, while this works in the supervisor mode. Okay. So, within the user mode, for the bottom 4 kilobytes, that is from the address 0 to 4095, is where we have the init code that is essentially loaded. Okay. So, it is just one page or one just holds one page frame or one memory block and comprises of the code part which is here and also the stack which is at this particular point. Okay. So, so this code essentially starts from the location 0 and the stack on the other hand essentially starts the highest address in the stack is essentially 4095. Okay. Now, in the supervisor mode, we have this 8 kilobytes region in the virtual address space, which comprises of the trampoline and the trap frame. Okay. So, right. So we have discussed this. We have essentially set up the virtual address space for this particular process. We now have two virtual address spaces, and what we now need to do is transfer control, right, from the kernel's virtual address space. So, essentially the kernel is executing. We need to somehow switch to the process's virtual address space and get this code to essentially execute, right. So, I have an animation over here which would essentially tell us the same thing. So, what we need to do to get this init code process to execute is that we need to move the program counter and the stack pointer to which is essentially pointing in the virtual address space of the kernel or the kernel's virtual address space into the init code and the into the init code and the stack for the init code in the user processes address space, right? And in doing so, there is also multiple transformations that need to be done, right? So first of all, we need to shift the virtual address space that is being operated upon from the kernel's virtual address space into the user's virtual address space, right? Second, we need to place the program counter and the stack pointer in a way such that the init code executes. Third, we need to switch from the supervisor mode of operation to the user mode of operation, right? Because we want this particular process to execute from a user space, from the user mode. Okay. So to repeat again, there are three requirements that we need to do. First of all, in no specific order, so we would need to change the program counter and stack pointer from the kernel space into the user's virtual address space. Specifically, the program counter should be set to 0. The stack pointer should be set to 4 kilobytes so that it grows downwards. Second, we need to move the mode of operation from the supervisor mode into the user mode, right? And the third is we need to also change the virtual address space from the kernel's virtual address space to the user's process's virtual address space. Okay. So, yeah, so there are multiple transformations that need to take place for this to essentially happen, right? And if we just focus on this part over here, right? So what it essentially says is the transformation from the main to finally when the init code executes, right? So the green part essentially says that the process is executing in the user mode, while the pink parts essentially tell you that the kernel is executing in the supervisor mode, right? So besides that, we also capture the two different virtual address spaces, right? The kernel's virtual address space and the process's virtual address space, right? So the sequence of function calls are as follows. So as we know from where we stopped, we've essentially looked at main, right? And the main essentially the last function that it invokes is the scheduler. Okay. Now the scheduler invokes the switch function, right? Now the switch function essentially changes the context of the CPU from the kernel's context to that of the init code's context. So recollect what the context means, right? So if I go back here, where is the context? Yeah. So recollect here what is the context. So context essentially is there is a pointer within the proc structure called the context, and essentially this comprises of the RA register, which is the return address register, the stack pointer, and the 12 S registers, S0 to S11, right? So these are the callee saved registers. So what we need to do to switch from one context to another is to essentially move between between one process's context to another using this particular structure. Okay. So if I go back over here, right, so we have two contexts that are essentially present, right? So the first is the we call as the scheduler context. So the scheduler's context comprises of the 12 registers, the RA register, and the stack pointer, right? Now what we do in the switch function is we switch the context to that of the init code. Okay, so recollect that the init code's not yet started executing, so most of its contexts are going to be 0, but it's very important for us to switch to this context so that later on it would permit like scheduling of other processes as well. So the switch function would change from the scheduler's context, that is the 12 plus 2, 14 registers corresponding to the scheduler would now essentially change to the init code's context. Okay, so this very important switch of context happens in this particular function called switch, swtch, right? Then switch now invokes forkret. This forkret is a function which is essentially on the way going towards executing the init code. Then forkret invokes usertrap.ret, and here between usertrap.ret and the userret is this important switch change again, right, where we essentially change from the kernel's virtual address space to the process's virtual address space, right. So this change is essentially done by in usertrap between usertrap.trapret and userret. Okay, changing from the kernel's virtual address space to the process's virtual address space essentially means that we need to reconfigure the SAT-P pointer, right. So recollect that the CPU in the paging or the memory management unit makes use of this SAT-P register, right, to which points to the currently active processes page directory, right. So while the kernel is executing, right. So while the kernel is executing, the SAT-P pointer points to the L2 page or the page directory of for the kernel's virtual address space. And what we are actually doing here is reconfiguring the SAT-P pointer so that now it is essentially pointing to the the init code's virtual address space or the process's virtual address space, right. So configuring the SAT-P pointer in such a way means that any address that you put that the CPU puts out now uses the corresponding page directory and page tables to transform from the virtual to the physical address, right. And this way we are essentially creating a new virtual address, or we are essentially configuring the CPU to use a new virtual address space. Okay. Now finally, in userret, we essentially are execute. So notice that userret comprises of both green and pink, and this is because userret essentially first starts executing in the supervisor mode of the process, right. Rather, it's first starts executing at this point where we have the trampoline, right. Now the trampoline has multiple functions. One is called the trampoline itself, the other is called userret. So the userret function is essentially present at this particular point, right. So in userret, you are now moving from the slowly moving from the supervisor mode to the user mode. Userret would essentially create the environment such that the program counter points to the virtual address 0 and the stack pointer points to 4096, and then sets the CPU in a way such that there is a transformation to the user mode, and then init code executes, right. So to execute one process, we have multiple functions that are invoked, such as the scheduler, switch, forkret, usertrap, ret, and userret. and finally Initcode that executes in the user mode. We also have switching from between different virtual address spaces. In this case, we are switching between the kernel's virtual address space to the process's virtual address space. Third, we are also switching between different context from the kernel's context to the context of the init code. And fourth, we are moving from the supervisor mode to the user mode. So, all of these transformations need to occur for the init code to execute.